Nearing right. Shots a little
Okay,
wide.
since you're live, yeah. No, do it.
Can you close the
Oh,
door?
I don't see the video on YouTube.
It'll be there in a sec. It takes a minute. That's my hair. You gotta zoom in there. That's my hair. I think that's it. Scoot back. Yeah, I'll scoot back. That's good, and then let me focus that. And yeah, I'll put that on. There it goes. How's the focus?
This thing is supposed to be cellular.
Oh, should we turn off the
Oh, good.
Yeah.
Thought I would then get your. Okay, 9 people are watching, so it exists somewhere. Alrighty. Yeah, 31 people on Zoom. Morning, everyone.
Am I muted?
Alright, you're unmuted.
Good morning, everyone. Welcome back to Chem 1A, summer 2020. We set up a new Zoom account for the course last night. I hope you guys got the announcements, and you can always join the Zoom from B courses. We have a link right at the top of the syllabus. But here's the new information. So if you're being contacted by friends, or if you're watching this and unable to connect to the Zoom, jot that down and take a screenshot maybe, because I'm gonna browse away from it. And we will hope to see you all there. When do we have it in Zoom?
90.
How many?
90.
90?
91.
Okay, so that's not so bad. So people are finding us. So we'll get started in that case. Ryan, can you go to Box and make sure this is on your computer?
Yes.
We might be able to do it in a short break. So last time we talked about amounts of atoms, molecules, a little bit about reactions, and we also discovered that we're on a journey together. We have a lot of things that we want to cover, and there's going to be a lot of discoveries we make together along the way. And working together in these small groups, and with me here, Ryan and Melissa and Christine and Jiho in your discussion groups, I think we'll have a lot of fun, learn a lot, and by the end of the semester, I think you'll be really good at chemistry. And in Chem 1, chemistry, we take a very broad view of what chemistry is. What I want you guys to be able to do when you leave this class is not just chemistry, not balance a chemical equation or figure out how many moles of glucose react with how many moles of oxygen. That's not very interesting. I mean, it is chemistry, but it's not very interesting, and it doesn't get you very far in your next courses down the line. So we want to expose you to that, make sure you can do the mechanics of chemistry. But I would rather, if you leave this class, and you could talk about the nature of entropy that we're going to talk about in a general sense. You could talk about energy balance in the universe and energy balance in our society and how to use energy effectively. And just be ambassadors of science, be fluent in science. We want to send you out for Berkeley. You'll have a fancy Berkeley degree, I hope someday. And people are going to look to you and say, hey, you have a fancy Berkeley degree. Can you explain this to me? And I want to be part of helping you get ready to explain science to the general population. So last time we talked about atoms, molecules. We're going to spend a little bit more time on amounts of stuff, and we're going to get to those areas that I think some of you were expecting that we would get to yesterday. But we're going to start right off with a chem quiz. So combustion of hydrocarbons, we talked about that last time. So combustion of a hydrocarbon with oxygen yields products which has this mass spectrum. So I'm wondering if you can predict from that mass spectrum which of these hydrocarbons we burned in oxygen. And think about that for yourself a minute. Melissa may mute your microphones to help you focus, and we will take a vote. When you're ready, Ryan, you should have the group of 4.
Yeah.
What would be really helpful is a group of 4 from last time. That's probably asking too much, isn't it?
I can do that. Do you want that?
If you can, for a short amount of time. I can probably develop it quickly too.
Just waiting for PowerPoint to load.
Okay, just start the poll running.
Yeah, poll's running.
Ready.
It's not having it today.
Okay.
I'm not sure why.
Don't worry about it. I can hear it also. They have this screenshot.
Mhm.
And can we get your share up there?
Yes.
You're putting your share in front of what? The screen?
It's giving me the universal file. It's spinning it.
While they're trying to boost you over Can you start Reef on other computers next to you?
Well, Reef is already started.
Both
No problem. You can do it. Okay.
It's from the Hydrocarbons.
Okay.
You can go ahead and screenshot. It's got the 4 and the are you ready for the responses? Yep. Yep, audience.
Okay, so about 108 of you responded in 2 minutes of thinking on your own. So let's review the question here one more time. Melissa will turn your mics on, and you can talk to each other. And I'll give you maybe something to think about. Remember I told you yesterday, burning a hydrocarbon gives you very specific products. You may recognize them in the mass spectrum. So can you balance a chemical equation? Can you work backwards to a mass spectrum? Work on that with your friends in your breakout room and see if you can come to a conclusion. Ryan will start the poll. Okay, we have about 75 responses, a few more of you. We're going to talk about it. Go ahead and click and Ryan, when you come back to me, don't let them come back to me. Don't display it. That's what's going to Okay. All right, so that's 100 responses. Ryan, if you could show us what people are thinking. So acetylene, C2H2, is the most popular so far, with A and B also having some people interested in that. So let's talk through it together. So what happens when the hydrocarbon is burned? Well, we talked about last time that I kind of expect you to know when a hydrocarbon burns in oxygen, it's going to form carbon dioxide and water. And hydrocarbons are the fossil fuels that are putting carbon dioxide into our atmosphere. We, breathing, put carbon dioxide into the atmosphere. All combustion processes do that. What you want to look at is the nature of the spectrum, and that peak at 18 was the relative amount of water produced, and the peak at 44, that's the mass of carbon, the relative mass of carbon produced. So that ratio, if it's methane, is 2 to 1, twice as many water particles, water molecules, as carbon dioxide molecules. And you can do that analysis for all those hydrocarbons you had. So C2H4, 2 waters and 2 carbon dioxides produced in the balanced chemical equation. So you get a 1-to-1 ratio of carbon dioxide to water particles. And acetylene, you get 1-to-2 relationship of carbon dioxide to water. So what you find then is the correct answer, as many of you thought, is acetylene. And that tells you any hydrocarbon that you burn that has a ratio of 1-to-1 hydrogen to carbon will give this kind of mass spectrum of the products. And if it's 1-to-2, you'll get the 1-to-1 ratio. And if it's 1 carbon to 4 hydrogens, you get the 2-to-1 ratio. So that's indicative of many hydrocarbons. And that's something of a problem because it's indicative of many. So which one is it? There are many hydrocarbons that have these kind of ratios. So we get some information from the mass spectrum, but we don't get enough to actually identify the actual compound. These could have been other compounds with these ratios of carbon to hydrogen. What we're really looking at here is something called the empirical formula. What we got from that experiment is the lowest ratio of carbon to hydrogen in this system. So we have a ratio of here 1-to-4, but there are several hydrocarbons that have that 1-to-4 ratio. These are molecular formulas. They're the actual molecule. This is an empirical formula. And it's called empirical because back in the day, and I guess still today, empirical means something that you went in and measured. You've got some empirical evidence. That's evidence that you can get your hands on. So the evidence you can get your hands on gives you this ratio, but it didn't give you everything. So there's more investigation that you need to do. So we'll just summarize that. In the case that we had, methane was the molecule of interest. Turns out these other molecules can't exist. Ethene and acetylene were the other 2 options. And we decided, simply because the ratio of carbon to hydrogen that was reflected in the mass spectrum, that was the empirical formula, and in this case, the molecule, because I told you the molecule we were burning. So let's move on then and think about, we've talked about this relative mass a lot last time. And we never said this word, mole. And this is the word I think many of you associate with chemistry. I'm going to go to chemistry class, somebody's going to say mole a lot. And I didn't say it at all. And maybe I won't say it again. We'll challenge ourselves. What the idea is to get from microscopic matter to bulk matter. So from the macroscopic properties of matter, macroscopic means the volume, the mass, things you can measure, to what's happening in the microscopic, the particulate world, the atoms and molecules. And we've already seen that the relative masses do that. So if I have, go back to the rock, paper, scissors example, if I have, I know every rock weighs 3 times what a pair of scissors weigh, then as you scale up, that relative mass, if you keep the same numbers, is always going to be 3 to 1. So if you have a 100 pounds of the rocks, you need 300 pounds of scissors to have the same number. Or if you have 1 rock, you need 3 pairs of scissors to have the same mass. So we understand the relationship between relative masses, and it could be mass or it could be just the number of things. There, when we said this mass of 100 pounds of rocks with this mass of 300 pounds of scissors, that was a 3 to 1 mass ratio, and we didn't really have a good idea of how many scissors and how many rocks were in there. We knew their ratio was 1 to 1, but we didn't know how many of each there were. There could have been a dozen, maybe a dozen rocks weighs 100 pounds. And then we'd also know that there were a dozen scissors, and a dozen scissors must weigh 300 pounds. So I said that backwards. A dozen rocks weighs 300 pounds. A dozen scissors weigh 100 pounds. So we don't know the actual numbers just from that mass, so we need a way to think about the actual numbers. And the actual numbers turn out to be not very important very often because we can't see the numbers of particles when we're talking about atoms or molecules. So we do just talk in dozens, essentially. A dozen is too small, so we go a little higher in number. What we do is we take the reference mass for everything, all our atoms and molecules. We pick one of our atoms, in this case, 12 grams of carbon-12, and we say that's going to be the standard relative mass. So if you have a relative mass relative to 12 grams of carbon-12, you have the same number of particles as that 12 grams of carbon-12. So if you have hydrogen, relative mass 1, relative to carbon, its relative mass of 1, there's the same number of particles in that 1 relative mass of hydrogen as the 12 relative mass of carbon. And you can put a mass unit after relative mass. So 1 gram of hydrogen has the same number of particles as 12 grams of carbon. What is that number of particles? Well, it's a ginormous number. It's, we'll call it N0, and instead of a dozen, we'll call it a mole. So this unit's mole is just a number, like a dozen, and you can calculate this number, and it's called Avogadro's number, and it's astronomically large, 6.02 times 10 to the 23rd, 6 with 23 zeros after it. So a truly fantastically large number. So in 12 grams of carbon-12, there are 6.02 times 10 to the 23rd particles. In 1 gram of hydrogen atoms, that's the relative mass, 12 to 1, there are 6.02 times 10 to the 23rd particles. That's the concept of mole. Wherever you would say relative mass, you could insert mole. So if I said 12 moles of carbon-12 have the same number of atoms as 1 mole of hydrogen, I could have said 1 relative mass of carbon has the same number of particles as 1 relative mass of hydrogen. And that's all we did yesterday. So those concepts are essentially linked. The only difference is when you, today we've just added the number, that's the number of particles in a set relative mass, so we can translate numbers to all those. So we're going to record molar masses in grams per mole. So the molar mass of carbon is 12 grams in 1 mole. The molar mass of hydrogen gas, H2, is 2 grams in 1 mole. So let's think about this for a minute in a chem quiz. 2 moles of an oxide of hydrogen. So here's 3 oxides of hydrogen. And oxide, as you might expect, means oxygen compound of hydrogen. Here's 3 possible ones. When you do a reaction, you do a reaction step on that, that compound releases a mole of oxygen gas and leaves behind liquid water. Which is the oxide of these 3? Think about that for a second. Melissa will mute your microphone so you think about it just briefly on your own. And I'm just going to give you just a minute to think about it briefly on your own, and then we'll get you in your groups. So, Ryan, if you could bring up the group of 4 on your computer and overlay the quiz, or you can overlay the poll.
Yep.
Are you ready?
Yeah. It's not working today.
It is not. Yeah, let's get a computer with more horsepower in there. For now.
Oh, this one says the internet connection is down. I'm on TripAdvisor.
Oh yes, get off the line.
Yeah. You want it.
Okay, but you're back here. Okay, so it's been about a minute. So if you haven't responded yet, go ahead and respond. And we'll get up to about 100 responses here. And what we're trying to do for you, and we're having a little bit of technical difficulty, we're trying to get the 4 main content slides up while you're thinking about the chem quiz. So the Reef software captures the actual chem quiz. So that doesn't have to be here, but this content might help you. So Ryan, if you could show us what people are thinking. Okay, so B is particularly popular. So let's go to the chem quiz. B is particularly popular. Talk about that amongst yourselves. We'll turn the microphones off. You can mute me, Ryan. And
Yeah, that should be with me better now because I got
Turn
it.
my
Does it need the
mic
glass
back
have a
on.
different
Yeah.
answer?
Okay, so go ahead and respond to this one. We don't have any responses right now. Are we having trouble with the read system? Are you online?
I'm up. Which
Ryan's up.
respond to the poll.
Respond to the poll. Someone respond. I think this is broken because I know people have responded. So that is anomalous.
Let's see if I can click it.
You might have to restart your. Can you just stop the poll and restart it?
Yeah.
If somebody could respond for us, I think iClicker is down.
Yeah. I responded and it's not telling me.
So can you just end your session? Are you logged in to the website? The website.
I
run
can
this?
do it from here.
Yeah.
I'll end the session.
End your session and come back in.
Okay.
So we're having trouble, as I think you can hear, my mic is on. We're having trouble collecting the responses. We'll see if Ryan can get back in. And she's ended the class and he's starting the class. And we'll turn on polling and start a poll again. If you could respond now, guys, if you're there. Okay, here we have the responses coming in. Apologize for that
Sorry.
little hiccup. We'll get these things worked out. We'll get a little bit more horsepower on the computers in this room. Okay, so that's about the responses we have. We got about 100 responses, Ryan. Let's see what the distribution is. And, oh my goodness, overwhelmingly. So the people who thought B, just overwhelmingly persuasive for this particular chem quiz. So that's fantastic. I agree with those people, and I think I will show you what I think. So for this chem quiz, we have an, oh my goodness, I'm not sure how I zoom. We have an oxide of hydrogen that if it were 2 moles of hydrogen peroxide, you would get 4 moles of hydrogen atoms and 4 moles of oxygen atoms. So the question is, how would you combine those to form an oxide? You know that the combustion products or the reaction products were a mole of oxygen and pure water. So you didn't know how many moles of water, but you knew it was water. You knew it was 1 mole of oxygen. And those ratios are appropriate. 4 hydrogens to 4 oxygens are appropriate for 1, 2 oxygens there, 3, 4 oxygens there, and 1, 2, 3, 4 hydrogen atoms there. So that's appropriate for hydrogen peroxide, and that is the correct answer. And I think we can see Lonnie do this in the lab. I so wish we were in Pimentel to see these. So
the reverse.
here's Lonnie.
The decomposition of hydrogen peroxide is spontaneous at all temperatures.
And that plume of gas was water coming off and oxygen coming off. And that's exactly
where he has a piece of aluminum.
The reaction that would go there. And you notice that reaction was catalyzed. The hydrogen peroxide just sits there. It's not doing that reaction. Adding the catalyst allowed the reaction to go. We have a question?
Mm-hmm. Is there a difference between hydrogen oxides and hydroxides? Is a hydroxide specifically OH?
The question is there a difference between hydrogen oxides and hydroxides? It's a classification problem. Hydroxide certainly is a hydrogen oxide. but hydroxide refers specifically to OH. So OH is a kind of hydrogen oxide, and its specific name is hydroxide. So let's go back and continue with our discussion here. So here's what we looked at last time. We had, well, here we have it not exactly the same. Here we have 2 moles of hydrogen reacting with, well, I can't say 2 moles. All I know is there's a 2 there. So that doesn't tell me how many moles, that's just a coefficient of the reaction. But it does tell me there's twice as much hydrogen as oxygen, twice as many particles of hydrogen as oxygen, and we've demonstrated that by the volume of the balloon. So there's twice as many particles here, they take up twice as much space, they're a gas, so this volume of gas, oxygen, would be smaller, and they form 2 moles of water. So they form the same number of particles as there was of hydrogen. So that's the same volume of a gas, same number of particles on the other side. So in this case, if that 2 refers to indeed a mole, then my touching of the screen is going to make me crazy. 2 molecules, or 2 moles of molecules, 2N0, that's Avogadro's number, react with a mole and 0 molecules of oxygen to give 2N0, 2 moles of water molecules. And we can say that is from the ratios in the balanced chemical reaction. So 2N0 molecules is 2 moles. So this is particles there. And I think what I need is an armband so my sleeve doesn't touch this as I go across. 2 moles of hydrogen molecules, 1 mole of oxygen molecules would make 2 moles of water. In this case, you could also do it by volume. And we'll learn later that if you're in the gas phase, the volume corresponds to the number of particles. That's why this volume is twice as big as this volume, and that volume is the same. You have a question?
Does having the same number of moles of H2 and H2O2 in different balloons equate to equal volumes? Aren't H2 and H2O2 different sizes?
So the question is, does the volume represented, this volume of H2 and this volume of H2O, they're the same volume, and is that really the same number of particles? Because water is a bigger particle than hydrogen. And as I was beginning to say there, these are gaseous particles. So in a gas, the actual size of the particle is incredibly small with respect to the whole volume. So with respect to the whole volume, the volume taken up by the actual particles is insignificant. So the size of the particle doesn't matter because they're scattered out. And a tiny particle of hydrogen behaves just the same way as a tiny particle of water in the gas phase. So there'll be, in terms of creating the volume, bouncing around and hitting the walls of the balloon, they do that in the same way and it results in the same volume. And we're going to talk about that, as I said, in detail later in the class. But now we know we could do also, we've done this before, we could use relative masses. The relative mass, 2 grams hydrogen relative to carbon-12, if we're talking about a mole, 32 grams of oxygen relative to carbon-12 as a mole of particles, 18 grams of water has the same number of particles as 12 grams of carbon-12. So those relative masses work out. And of course, I need 2 relative masses because I need twice as many particles of hydrogen as oxygen. So that mass ratio, 4 to 32, gives me 2 particles to 1 particle. And 2 relative masses of water give me the right number of particles. And notice, like I said, you can, if you'd like, replace relative mass with mole. Those have the same role in all those steps. Now, you should notice, though, that the number of molecules is not conserved across the chemical reaction. We have 3 molecules on this side and 2 on that side. So there's no conservation of the number of molecules. The liters of gas, also not conserved. The number of moles, not conserved. 2 moles plus 1, that's 3 moles of particles over here, 2 moles of particles over there. Those things are not conserved, and you can't assume across a reaction that you're going to have the same number of moles on either side, the same number of particles on either side. What you can assume, absolutely, especially in Chem 1, is that you'll have the same total mass on either side. Mass is conserved. And going, if you take the full mass on this side, it has to equal the full mass of all the particles on this side. So we'll show you that. Mass is conserved. 2 times 2 is 4, plus 32 is 36. 2 times 18 is 36 grams. So mass is conserved in chemical reactions. If you take nothing else home from Chem 1A, take home the fact that mass is conserved in chemical reactions. We can't eliminate mass or create mass in the chemical reactions that we're going to do in Chem 1. Here's a little bit about conversion factors, and I think what I'm going to do is have your teaching assistants go through this part of this lecture in the discussion sections. So I will give them this set of slides. They can use either this set of slides or just give you a little primer on conversion factors. This is dimensional analysis. That means you use dimensions like miles and feet. Those are the dimensions of things. And you convert between the dimensions. And I just have some slides here that go through this. Here's some dimensions, mole to particle. Those are different dimensions. So you can write those things as ratios. And when you write them as ratios, when you write an equality, 1 mole is so many particles as a ratio, then that is unity. So I divide 6.02 onto this side. That leaves 1 on the other side. So each of these conversion factors have unit value, and you can multiply anything by 1 and not change it. 1 is the multiplicative identity. I'll try not to say math stuff like that, but that means you can multiply anything by 1, and it doesn't change it. It changes the dimension. It changes feet into miles, but the distance, 1 foot or 5,280, 1 mile or 5,280 feet, that's the same distance expressed in different dimensions. So we'll have the GSIs go over that a little bit for you, and I'll flip through this relatively quickly. I might stop here for a minute, though, because this tells you something about the size of a mole, just that number of particles. So let's say you hit the lottery big time, and the value of the lottery is a mole of dollars. So Powerball has been going on for about, let's say, 1,500 years, and it keeps going up. And the big hit has yet to come. Somebody hits it and it's a mole of dollars. And when I say 15 years, Powerball can't even grow that fast. It would probably be something like 100 million years for Powerball to get to a mole of dollars. But let's say you win, and then you go on a crazy spending spree, spending $1 billion a second. I would love that Amazon spree. Go to Amazon, $1 billion a second. You can't load your cart fast enough. How long would the money last in years? Well, this is dimensional analysis. $1 to years. $1 billion a second to years. So we can just go through that. If you have a mole of dollars, that's 6.02 times 10 to the 23rd dollars. And if your spending rate is $1 billion a second, and that's what we've demonstrated here, $1 billion per second, then you convert to dollars per year from dollars per second. And the way you do that is say, well, I have $1 billion per second. I'm going to multiply that by a unit conversion factor. 60 seconds and 1 minute. Those two things are equal. Their ratio value is 1. I haven't changed this. I've just changed the units from seconds to minutes. I can change the units from minutes to hours with this conversion factor. 60 minutes in an hour. I can change that to days, 24 hours in a day. I can change that to a year, 365 days in a year. All these values are 1, and I'm changing the dimensions of this number, but not the value of that number. So I can then cancel units, seconds with seconds, minutes with minutes, hours with hours, days with days. And I'm left with just dollars per year. So now if I multiply all these numbers together, I'll be in dollars per year. So that number is 3.15 times 10 to the 16th dollars per year is what your spending rate would have to be. So this many dollars times this spending rate, that's how much you won. This is your spending rate every year. You spend 3.15 times 10 to the 16th dollars. It would take you 1.9 times 10 to the 7 years to spend all your money at $1 billion a second. So Jeff Bezos would be out of money. What is Jeff Bezos? 150 billion, it's something crazy like that. So Jeff Bezos, 150 at $1 billion a second, he'd last 150 seconds, so 2 minutes. You win a mole of dollars, your $1 billion per second would last you 10 to the 7th year. So something like 10 million, in this case, 20 million years. Waiting for that one. So let's look at a demonstration here. I'm going to burn phosphorus in oxygen. So let's watch Lonnie do this in the demo lab. This is just fantastic in Kubinec. Lights up the whole building. So
we're in the demo lab with Lonnie, where he's going to produce a phosphorus oxide from pure oxygen and pure phosphorus. The pure oxygen will come from liquid oxygen, which he's pouring into this flask. That will drive out all the air and leave an atmosphere of pure oxygen inside the flask. He also has a piece of solid phosphorus attached to the end of a string that he can lower into the bottom of the flask. Now this flask contains oxygen and phosphorus exclusively, and they're going to react. The question is, will the phosphorus be used up first and have oxygen left behind? That is, will phosphorus limit the reaction? Or will the oxygen be used up first and there'll be phosphorus left behind, where oxygen limits the reaction? Oxygen can be the limiting reagent because when it's used up, the reaction has to stop. Or phosphorus could be the limiting reagent. When it's used up, the reaction has to stop. Lonnie's waiting for all the oxygen to evaporate, and when it does, he'll warm an iron rod and touch the phosphorus to initiate the reaction. Looks like he's ready to do that. Here's a warm iron rod that he'll touch to the solid phosphorus. When he initiates the reaction, you'll see a tremendous amount of energy released as the phosphorus oxide is formed, and the energy is released in the form of bright light, tens of kilowatts of light, the equivalent of hundreds of 100-watt light bulbs. Lonnie can use the light actually to read from one of his ancient tomes. Now, Lonnie's told me that the ink in some of these ancient tomes is only visible under the light from the phosphorus oxide reaction. I don't know if I believe that, but I can see that he can clearly read from the light from the phosphorus oxide reaction, the reaction of phosphorus and oxygen to form phosphorus oxide.
Okay, so you saw the reaction there. So let's go back to a chem quiz about that reaction. So 31 grams of phosphorus is what Lonnie put in the bottom of the flask. It formed 71 grams of a phosphorus oxide. What's the empirical formula of the phosphorus oxide? You don't have to get the exact formula, you have to get the ratios correct. So think about that for a second in your muted breakout room, and we'll take a vote. So are you ready with the set of 4?
I am.
And the quiz running?
Yes.
Fantastic.
Oh, no. Disconnecting. Oh, how disappointing. But
We have to go through this tonight. Bring the other computer down and see if we can keep this connection alive. Aaron, or Ryan, or on, or sharing. Can you mute me? Okay, we have about 70 responses. If you haven't responded so far, go ahead and respond, and we'll see what you're thinking. Let's see if we can get 100 of us. There's 90. There's 100. Ryan, let's see what those 100 people are thinking. Equally split between A and B, so this should be an interesting discussion. Melissa, turn on their mics, and let's have a discussion on that. Ryan, you can start the second poll. Okay, go back here.
that was on purpose.
Oh, you wanted to give them back?
Yeah.
The leaf turned over.
Leaf shows whatever I want.
Now, did it screen capture, or did it screen capture right when you started the...
It's screenshot captured right when I started the call. And so I just have to start it on that side. And now I can go back here and they're still looking at the
What does it
question.
look like? I thought you might have started it on the group before.
Yep, I didn't. That's it.
Hi, did you guys discuss your answers yet?
Is that the active one? It's hard to tell.
Okay, well, what did you guys call?
Great, guys. You had a few minutes to think about that. So let's go back to the.
You want to see the numbers?
Oh, let's look at. I'm sorry. Ryan has to show us the numbers first. Oh, we didn't decide. Interesting. There was um, no swing from one side to the other. A and B are still equally popular, so we really do need to talk about this one a little more. So 31 grams of phosphorus, 71 grams of the oxide. I apologize. I don't think I swiped enough through here for you guys to have the molar masses of the phosphorus and oxygen would have been helpful here. You're online, you can bring up a periodic table. But in general, I'll try to have all the information you need here as well, so you're not having to search the internet for information. So I'll make sure that happens in the future. But how does this work? You're putting together phosphorus and oxygen to make a phosphorus oxide, but all of this stuff is unknown. The number of phosphorus atoms that react with the oxygen atoms or molecules to give you the phosphorus oxide. But you do know there were 30 grams of phosphorus about, and in order for that to form 70 grams about of the oxide, that means 40 grams of oxygen had to react. So that has to be true. Mass is conserved. So the mass ratios are 30 grams to 40 grams. And you know, from mass ratios, we could go right with relative masses to the number of moles, and then that's number of particles, and we could skip the moles part, just go right to the number of particles. So what does that look like when we do that? There's the mass ratios. Here are the molar masses. I apologize. That was supposed to be on the first slide. 31 grams per mole of phosphorus. There's, and we decided there were about 30 grams of phosphorus in the reaction. So 1 mole, 1 relative mass of phosphorus was there. So the mole ratios, 30 grams of phosphorus times 1 mole for 31 grams of phosphorus, that's the molar mass, 1 mole. So that's how many particles are there of phosphorus. Do the same thing, you deduce there were 40 grams of oxygen. And that 40 grams of oxygen, 1 mole, is 16 grams. That's 2.5 moles of oxygen. So the ratios are 1 to 2.5, and that has to be the ratio in the final product. Of course, 1 to 2.5, that's not how we write molecular formulas. So that is kind of the empirical formula, but let's multiply those both by 2. 2 to 5, 2 particles to 5 particles in that compound is an empirical formula for that compound. So from mass ratios to mole ratios using the relative molar masses. Turns out the actual compound is P4O10. So we found only the empirical formula, and the answer here is B. So nice work on that. I'm gonna skip this one all together. You guys can look at that online. Maybe we'll post that. In general, we don't, as you know, if you download the JPEGs, we don't provide you with the chem quizzes. In the chem quizzes are something you're supposed to see initially when you get into class. You can take a screenshot of that. I'll give you the actual plots. You can take a screenshot of that if you'd like and talk about that one on your own. Right now, we'll go to a break and short commercial. You guys can go take a bathroom break or grab a brownie, whatever it is you do, and we'll have a short commercial moment. So, Avery. Here's Avery. Avery is our Chem 1A dog. Avery, come over here. Good girl. Sit down so you can see the camera. Good girl. Avery? We have Avery and quiet moments, calming aid. Yes, quiet moments. When your dog is stressed, try quiet moments. They reduce stress, make your dog happy, and dogs just love them. Quiet Moments, Senior Wellness, Calming Aid. At your local drugstores or on Amazon.com. Okay. Stop showing my socks. Okay, guys, we're back. Be sure to get your quiet moments. Calming Aids, our #1 sponsor. So let's continue through this one. Oops, if I continue through it like this, you're going to see the answer. How do I can't actually skip ahead, darn it. I'm going to try and not show you the answer. Okay, so we're going to start the next series. That's why we took our little break. I'm going to take a little drink. Ryan, can you mute me so they don't hear me gulping? You know what you should do? You should just get this up and take a screenshot of it yourself. So you can just do a JPEG view. You want to bring it up. So you have to open and close PowerPoint. Are we live?
Yes.
I'm unmuted.
You're unmuted.
Okay, we're going to continue our discussion. We've talked about amounts of stuff so far. Now I want to talk about amounts of energy. So stuff and energy are what we talk about for the entire class. So I wanted to introduce some stuff and energy introductory material before we get into the real content of the class. It's all real content of the class, but this is kind of the machinery, the basics that we need to know to move forward in the class. So energy, heat, and temperature. By the time you're done with this class, hopefully by the time you're done today, you should know the difference and be able to tell people on the street who might know you or not want to know you after you tell them this. Energy, heat, temperature, and work are different things. You should be able to say the difference between those. In chemistry, and when I teach chemistry, I use very precise language. That means I say a word that means an exactly precise thing. I will not mix up heat and energy and temperature. I will always use the exact right word, I hope. And you need to know what that word exactly means so you can follow along. So let's talk about energy to start with. Energy is present in matter based on a couple things. It's frequently contained in matter because of the arrangement and the motion of the particles in that matter. Energy is something a substance can contain. It can have that energy. It can transfer that energy. It can absorb energy. Energy is an extensive property. When I say the word extensive, I mean it relates to the extent of the system. If you have a pound of rock, it's got some energy in it. 2 pounds of rock has twice the amount of energy. So it depends on the extent of the rock that you got, usually the mass. So in this class, we are really frequently going to do this, and I already touched on it last time. We're going to plot energy on the board, and we're going to put energy states on the board. These are 2 energy states. In this case, a high energy state, and I've labeled the final state with that little f, and the initial state with that little I. Changes in energy, we're going to talk about all the time. And I'll tell you right now, all we talk about is changes of energy. The total amount of energy in a system is often very hard to determine. It's very complicated how the substance maintains and stores its energy. So the actual amount, we're not usually concerned with. When a process happens, we're interested in the change. The changes we can tell, because the change, something happens and we can make a measurement. So changes in energy are what we want, and in this case, going from the initial state to the final state, what is that change in energy? Well, we use the symbol delta for change. So pretty much for the rest of the class, you're not going to see E's without a delta in front of it, because changes are all we talk about. So delta E is the energy state of the final minus the energy state of the initial. And that's important because final minus initial imparts a sign on the energy change, a plus or a minus. Energy itself does not have a sign. There's no plus energy in anything or minus energy in anything. Changes can have a sign. Energy itself does not. So we measure energy in a unit called joules, and we'll use that energy unit a lot. In this case, final minus initial, the final energy is more than the initial energy, so this difference is bigger than 0. delta E is positive in this case. So we have to define now a couple ways to track energy, because really all we do is track it going from one place to another. We track the changes rather than the absolute amounts. So we define, to track energy, a system and the surroundings. The system can be whatever we want. It can be an individual molecule. It can be the water in a flask, be the gas in the room. We define it rather precisely, and then everything else is the surroundings. Energy can move between systems and surroundings. We have to define the system very precisely so we know where the energy is going. And if we measure an energy, all that energy was coming from just the system. So we get the system's energy change. So in this case, the system, I don't know what it is. It could be a rock, it could be a scissors, it could be paper, it could be a balloon of gas. It could be it could be a quiet moment dog treat. Any of those things could be our system. In fact, it'd be interesting to know how much energy is in a quiet moment dog treat. We'll be able to design an experiment before too long to figure that out. A couple, because Avery ate one. So our system was originally at low energy. There was some change that occurred, and it went to high energy. One of those changes that could have occurred, or one of the ways it could have gone from low to high energy, is to absorb heat. So now we've got our second word, heat. Heat is how energy is transferred. It's the method by which energy travels. Heat is not energy. Energy is something a system contains. Heat is how it exits and leaves. Heat will have the same units, joules, because a joule of heat leaves the system. The energy of the system goes down by a joule. So the units are the same, but don't let that confuse you that they are the same thing. So in this case, heat entering the system raised the energy of the system. And you might intuitively have thought that's the case. You heat something up, you put a beaker on a burner, and it gets hotter. That's temperature. Temperature is kind of a measure of energy. So heat traveling in, I think intuitively you would have guessed that the energy would rise. How would we notice it? Well, we might notice it. We're going to give heat the symbol Q. And in this case, I'm going to put a plus sign in front of the Q. Now, there's no plus or minus heat, just like energy. There's no plus or minus energy. That plus sign simply means heat travels. Plus means it's coming into the system. And it's easy to remember in a sense because that Q is plus. Heat coming in tends to make the energy higher. So it's adding to the energy, plus heat. So that heat comes in. The system changed by that amount of heat. Joule for joule. 100 joules of heat came in, the change in energy of the system, and just the change of energy in the system, not the energy of the system, changed by those 100 joules, that amount of heat. And we understood that was greater than 0. So we call those kind of reactions endothermic, or those kind of processes. Endothermic, you can probably, if you know Greek, if you are familiar with your ancient Greek, endo, into, thermic, temperature or heat. So endothermic, heat going into the system. So where does that energy go? It goes into the motions of the particles in the system in general. We'll talk about other ways energy can be stored in the system. But that heat makes the molecules in the system move around more, so that heat energy is somehow transferred into kinetic energy, motions of particles. Now, motions of particles in the system is how we measure temperature. So now temperature is not an energy and it's not a heat. It is a measure of the relative motions. You have more motion in your system, you have a higher temperature. A temperature change can come from a heat change. Temperature change can come from an energy change. That's what we have, these three precise definitions. So in this case, the energy change of the system directly proportional to the temperature change. The energy increased and the temperature increased because heat came in and gave us more molecular motion in the system. Temperature in general is a measure of how much energy is in a system, the kinetic energy of the particles in the system. Of course, we could do it the other way. Delta T, anytime we have a delta, is T final minus T initial. And in that case, that's also bigger than 0. We measure temperature in Kelvin in this class. That's the absolute temperature scale. So 0 in temperature is 0 Kelvin, and it goes up from there. There are no negative Kelvin degrees. You'll learn about that in your discussion sections and in your homework. We could also have heat leave the system, and notice for this heat, I've given it a minus sign indicating it's not minus heat, it's not negative heat, it's just that it's leaving the system. So that heat leaves the system and the system drops back down in energy. So go through that one more time. Heat leaves, the energy of the system drops, the motion of the particles would get slower, the temperature would drop. In that case, the energy change in the system is still equal to the heat flow, both in joules, and in this case, less than 0. Correlates with that minus heat, that heat leaving the system. Exothermic, there's exo, that prefix, meaning out of, leave the system, negative heat, negative change in energy. Again, proportional to delta T, and in this case, delta T would also be negative. A key thing to take home is this relationship right here, that in all these processes, energy is not lost. So if a joule of heat goes from the system to the surroundings energy goes up by a joule, the system's energy goes down by a joule, but the changes in both of them are the same in magnitude. They're different in sign because one has to go up in energy and the other has to go down in energy. But the magnitude, the number of joules, has to be the same. It's one statement of the first law of thermodynamics, that energy is conserved just like mass. Energy, consistent in this case with random motion. Not always, but in this case. So we can do heat flow and energy change and look at this a little more carefully. Heat capacity is a measure of how heat moves from system to surroundings. It's how much energy a system can absorb and before it changes in temperature, or how much energy it can absorb per degree in temperature change. So it's the capacity to absorb heat. Something that has a high capacity to absorb heat absorbs a lot of heat before the temperature changes. If you have a low heat capacity, a low capacity to absorb heat, then heat comes in and your temperature changes a lot. It's analogous to filling flasks. So flask 1 here and flask 2, flask 1 has a low heat capacity. Oops. Let me go back just a second. Flask 1 has a low heat capacity because a small amount of energy created a large change. And this is very similar to a flask with volume. And you would say, I'm pouring liquid into these flasks. So let me just do a quick check-in here. I'm pouring liquid into a flask. So this one, just quickly talk about amongst yourselves. Well, let's do a few seconds of talking and see what you think. Pouring fluid into the flask, is that an example of something that's exothermic, or it really doesn't have any relationship? Or is it analogous? It's not exactly, of course, you're pouring water, but what process is analogous to? Exothermic, it's not analogous to any energy relationship, or it's exothermic. If you'd start the poll, Ryan, we'll just take a minute. This is just a quick check-in. There's a question.
What's the difference between specific heat capacity or just heat capacity?
The question is there a difference between specific heat capacity and heat capacity? Specific just means per mass. Heat capacity is how much your temperature is going to change when you absorb heat. You could do it by the amount of substance, the mole of a substance, by the liter of substance, by the any amount of substance. Specific heat capacity refers to specifically by doing it by mass. Okay, let's see what they're thinking. I'll give you the screen share. Hopefully that just works. Yep, go ahead. You got about 100 responses. The answer is most popular is A, endothermic, and I love that. I think you guys are thinking about this. If we're treating water going into a system and you thought of water as energy flowing, energy does flow by heat into the system, that would be an energy flow into the system, an endothermic process. So if I allowed heat, that is, we're talking about the analogy, plus heat, and the temperature is analogous to the height that the water gets to in the flask. So you can already see that the volume is proportional to the amount of energy involved. So this one, a high change in temperature for a small volume, high height, small volume. So you poured in some water, the height changed a lot, wasn't that much water. Got a big temperature change for a low energy transfer. And of course, if your flask is big, then if you pour in heat, you have to pour in a lot more volume to get that same temperature change. So a lot more heat had to go in. That's a high heat capacity. It holds a lot of energy per unit temperature that it changes. We quantify this with this little relationship. The amount of heat transferred is equal to the amount of substance. In this case, it is the mass because it's a specific heat capacity, mass-based heat capacity. You can also do it by mole. In fact, that could stand for mole or mass. You take the amount times the heat capacity in units of gram per mole, or excuse me, joule per mole or joule per gram, multiplied by the temperature change. So amount of heat causes a temperature change based on the heat capacity and how much substance is there. Relatively straightforward reaction, and here are some. heat capacities. So here I've written specific heat capacities by joules per gram degree Kelvin, and here molar heat capacities, joules per mole Kelvin. Something really interesting comes up right away, that you'd expect different substances to have different heat capacities. And indeed, they have different specific heat capacities. But interestingly, most metals, by the mole, change the same with heat absorbed. They change the same temperature when they absorb heat. And you can think about that on your own, what that might be, but metals, very rigid structure, very similar structure between one metal and another. The heat capacity is not related to the kind of particle, but the fact that it's just arranged like a metal. Here's some other things: graphite, some alcohols, chloroform, water. Water has a particularly high heat capacity, 75 joules per mole Kelvin. One of the largest on there, this ethanol, has a slightly higher molar heat capacity. But those are just to just give you a number about how that works. So you have to add about 4 joules to a gram of water to get the temperature to increase by 1 degree Kelvin. Can you step out of the program so I can show you?
Yeah.
It's right on the table. So we will, we're running down towards the end here. I think what we'll do is, let's just talk about this chem quiz together. We won't do the 2 votes, just the 1 vote. Talk about this with your neighbors in your groups. I'm going to take super hot metal, and I'm going to drop it in a cool water. So a kilogram, same mass as a both. A kilogram of cool water, a kilogram of hot metal, molybdenum in this case, molar mass 95. What I'm curious about is both of them are going to change temperatures. Basically, they're going to come to the same temperature. Which will experience the greater temperature change? Will the metal temperature change be greater than the water? Will they be about the same? Or will the metal change less than the temperature change of the water? Talk about that. Start the poll.
Let's start.
And you're talking about it in, you don't have to think on your own this time. We're just going to take a quick chat. Ryan, if you have the group of 4, I will go to your share.
I don't. I have the quiz. Would you like me to have the quiz?
If you can.
Yeah.
Yeah, and then I'll start the quiz and go to the group of 4.
What's up?
Hopefully we'll figure out how to keep sharing. Can you go full screen?
Yes.
So some information you might find useful. Over here, all the definitions over here. Okay, that's a lot of you already in just 2 minutes, so let's see what you're thinking. Ryan, if you can just give us the results there. Split between A and B again. Some people think the temperature change is going to be about the same. Others think that the metal is going to change more than the water. That is, the magnitude of the temperature change, more degrees Kelvin than the water. Let's just work through that. So the heat that leaves the metal is absorbed by the water. So it's a system surroundings kind of thing. You could call the water the surroundings. Every joule of heat that leaves the metal is absorbed by the surroundings, joule for joule. The number of joules of heat is the same for the system and the surroundings. Joules go in and joules go out. So this is magnitude of heat. When you absorb heat, this is how you absorb it. You absorb it by your heat capacity and temperature change. So both of those things we know. We know the heat capacity. We don't know the temperature changes of these two, but we do know the relative heat capacity. So you can probably guess then, I can just do some cross multiplying here and see that the ratio of the heat capacities gives you the ratio of temperature changes. And we saw that the molar heat capacities of the metal were around, or the specific heat capacities of the metal, you can calculate that, is 1/4 joule per mole for the metal, 4 joules per gram, it said mole, 1/4 joule per gram of the metal, a 4 joule per gram for the water. So every joule that the metal loses doesn't raise the water by the same number of degrees. So the ratio of these two things, ratio of heat capacities, is 16. So the temperature of the metal changes by 16 times the water change. The metal temperature comes crashing down and the water barely changes temperature. The water has a big heat capacity. It can take all that heat and not change its temperature. The metal has a low heat capacity. It delivers a ton of heat and its temperature changes a lot. Okay, if I could just show you one thing. Tomorrow, if you guys could bring a rubber band class, and to class, I mean to your couch, or if you even get out of bed, I don't know, have this on your bedside table. This is just a standard, pretty big rubber band. You find them on, binding vegetables and stuff in the market. If you don't have one, that's okay, no big deal. You can, by virtual Zoom, see what your Zoom roomies are doing. So that's all the time we have. Quick question.
Can you give a more precise definition of enthalpy?
Enthalpy?
Mm-hmm.
I haven't said the word enthalpy.
I think in the chat there's some discussion about what enthalpy is.
Okay, the question is, can I give a precise definition of enthalpy? And I'll tell you, I'm going to delay that, and maybe if you'd like to come to my office hour and ask about enthalpy. I don't want to bring in words that we haven't covered. We'll get to the word enthalpy later. All you have to know so far is just energy. I don't mean to put you off. Turns out they're super similar. So we'll see you next time. Any other quick questions before we go?
Your office hours are now.
My office hours are now posted.
They're now.
My office hours are now. So our helpful student coordinator says, you have to answer that guy now, or girl or person now, because your office hours start now.
Well, we'll stop the live stream.
We'll stop the live stream.
Then,
we'll keep the Zoom open.
Yeah, I like that plan.
Well, wait. But they won't be able to see me because the live stream is using this camera.
We can connect the camera to the Zoom.
Okay, here's what we're going to do. We're going to stop the live stream, start a Zoom.
Same Zoom.
Same Zoom. Stay here. We're just going to switch the camera from the live stream to the Zoom, and the girls are
if you want office hours.
Making fun of me because I have to answer the question now. Anyway. All right, do that switch. Everybody just wants to stay for office hours. Please stay for office hours. You'll now have to ask questions. The live stream is over. You'll now have to ask questions through the Zoom chat rather than the live stream chat. And we can talk about those things. Let's see if we know.